that looks like another planet. Yeah, you look closely at the geology of the Sahara, and like, I could not. And it's been, Star Wars used that. It's another planet. It really is just it's a lot.
Yeah.
But yeah, it's the same activity, right? The same, but the like.
All the new things to look at.
But the visual footprint of it, like comparing the Amazon and each air, is so different.
It's like another planet.
Yeah. So about the geology and the land cover and back to the neato.
Yes.
So
Yes.
no, I don't think I'm going to get to it.
Yeah, I see you moving for the rest of your
I know. Yeah.
But I see your
Yeah, I mean, it's a challenge. I would go harsh.
Hello, Harsh.
Hey, how are you? Yeah.
And apologies in advance, I had to run to another meeting.
Well, thanks for saying hi.
We didn't get going to connect this week, but going to do it.
Yeah, when it's not to pull out.
Yeah, yes.
But yeah, making the connect, especially here, so that's many different, all the organizational human factors challenge actually bringing the data and technology to the supply. One of the keynotes at SAT Summit is like actually show me what a decision maker looks like. One that's like one that's like gets data, analyzes it all, and then it comes to like the data-based decision. It's like it's a myth. It doesn't. I mean, maybe you've but in some ways, like how decisions made is not like it's very complicated.
Yeah.
It doesn't happen at one point in time. A lot of decision can be made and then unmade. It goes through all bureaucracy.
And I feel that when you make a decision, the decision was even previously we have your unconscious part of the brain. You already took the decision before you know it.
I mean, there's something to like inform, like priming your intuition. But yeah, there's also like just confirmation bias, like, oh, that report looks like it was facts of what I want to do.
Okay, so you go first.
Yep, I'll take like 15, you take 15 or so, and then see what kind of discussion we have. I mean, yes, it's just 10:30 now, which is like the scheduled start. We'll give a couple minutes for see if any more folks, but very happy to get started in a couple minutes. If you look at the schedule, there's like a 2-hour block. We're not going to talk for 2 hours. We're going to we'll do, like I'll do 15, Bruno will do 15, and then we'll kind of open up for discussion. So 45 minutes an hour, and yeah, we'll give like 2 or 3 minutes to any late arrivals.
Hopefully we have a lot of questions.
Yeah, any questions?
Because I guess if not someone else, we talk about PvP.
Yeah.
About what?
Oh,
I'll mention it at the outside. While we're waiting, is most of them from the bank or from other institutions, or no? You all, where are you coming from?
I'm just saying, I come from a authorization service provider in Europe, GAF AG in Germany.
Okay.
I'm based in France, but
Oh, awesome. Okay, great. Yeah. And how about yourself?
From the bank as well, London geospatial specialist at the urban practice for West Africa.
All right. Okay.
Does the ghost team still exist?
Ghost. Yeah.
Yes, it does. Yeah,
You're talking to.
it's on the 4th floor, I think.
With Ben.
Oh, yeah, Ben.
Ben is still the Keith left.
Yeah, Keith. He's actually in the city. He's in the south town.
Yes, that's
We know you.
and then you work this out.
But it's part of the IT mission. I think
Oh.
Stella.
Stella Mokan.
Yeah.
You are Bruno?
Yes.
Oh, okay, so We connect online, we connect.
Yeah, yeah, yeah.
Yeah.
That's the group that I told you guys in the email. That
Yeah.
is.
Yeah, she was the one who told me. So that's what
Oh, great.
It's not, somehow it's not in the program,
Yeah.
but it is part of the conference. So thank you for coming.
No, I registered for the whole land conference and managed to go to a single session.
Well, that's, I mean, that's your prerogative being working here. Oh, we know your partner is at Mapbox.
Yeah, but I'm an AI engineer. I also work with Han under several supervision, and we are working on AI engineering applications. And
There's AI engineers at the bank now. That's amazing.
well, we have some of our team,
Different units.
That's awesome. Wow.
and most of us came from private sector, so and from a very diverse background, like big companies, startups.
Wow, congratulations. This is awesome. Are you part of the ITS division?
Yeah.
That's cool. So this is actually a fairly technical room. So we can get into it, but you are with us.
Yeah, with playing.
Love.
And you're here for assist on AV. Cool. We're just kind of getting a sense of who's in the room. So yeah, where you coming from?
Hey, I work partly with Chairman's team in FCB, and then I'm also working on a geospatial project that is looking at some deforestation models.
Great.
Sorry, mix of two things.
Cool. Hey, we're just going for now.
I'm Tisha. I'm a data scientist in the digital agriculture team in the agricultural office.
With partners?
Yes.
Yeah, nice. Good.
Great.
I'm Katie. I work in the dev data group. I just joined. I'm organized, yes, and I'm in both science.
This is awesome. I mean, like, yeah.
But Manish also told me that.
Yeah, it was
Good. I said
You said them. Oh, good. Yeah, I didn't get to it. So yeah, this is great. Like we can, this is a room we potentially can get into some of the like, technical stuff as well. And I think you'll have some of the like real basic, some advanced context in what we're talking about. So yeah, we'll do. I'll go through slide like 15. Bruno about 15. We'll have discussion. Hour max. We're not going to take the whole 2 hour block. So. These are
You want to speak the DDP a little bit? Or do you all know what data partnership is?
yeah, I got it. Yeah. So this is a visualization from Amazon Line Watch, which is I'm Mikhail Marin. I work with Earth Genome, and what we're seeing here is detections of artisanal mining across the Amazon. And the point I'm trying to make here is they are very pervasive to pervasive, small. If you want to search and monitor them, it is good if you have help. Doing this using human analysis is beyond what you can do, and I'll talk a little bit more about it, but we built this using custom trained machine learning models fairly quickly as you can today, but through the use of foundation models, we leverage play builds, doing this kind of applications and other applications is getting even faster because of the necessary preconditions of the training and the machine learning engineering that you need to do up front. There's more and more models that you can leverage out of the box to do this kind of work. So that's what we call generative AI. So there is some parallels with large language models, but also distinctions. But really, there are these general models which can fit a lot of purposes, and if you tune them in the right way or label them in the right way, very rapidly you can apply them for all sorts of purposes. I work at Earth Genome, I lead product, and we're small, nonprofit, 15 people or so. We work very closely with scientists, with people working in policy, journalists and others, and we focus very much on environment and climate. And so have a really firm footing in the science and policy of environment and climate, but also very firm footing in the latest in technology for Earth observation and mapping and visualization, and try to connect the two. So we have a large number of projects, such as the Plotline, which is a focus exclusively on food, the future of sustainable food, and doing new kinds of modeling and visualization in order to get insights. We've built Global Plastics Watch to find plastic waste sites all over the world. Again, that project was using a custom trained model. And we are part of the Climate Trace Coalition, which is working to do facility level emissions globally. So every steel plant, every part of oil and gas transport, every acre of deforestation or reforestation or rice fields, there's a whole combination of sensors and modeling which comes together, and we're part of building that data infrastructure and presenting the data to the world. And so from this has really driven us to build tools to find things quickly. It's very much a common need to find. You all know you're trying to do this every day. Bruno and I came over from another conference this morning called SAT Summit, and one of the keynotes there's talking about like the EO bubble that we're in, the amount of resources and sensors and data is exploding. This gives you, this is the number of just massive expansion of satellites observing the Earth, which are in orbit. And how do we then scale what we are doing to use that data, analyze that data, in order to apply it for the problems we need? That part also needs to scale up the availability of data. This is a great problem to have. And as you all know, because I get the sense that everyone here is working in this intersection, connecting these data sensors to when it is actually going to solve a problem directly on the ground. And this is, this is in Brazil, police military action to prevent deforestation. Thankfully, that needs to be, that is informed by data. And so, but making that connection is a huge effort. There's a ton of organizational and human factors and technological factors as well. So like I said, when we built Amazon Binding Watch, this was a custom model. We largely work with Sentinel-2 because of its comprehensiveness and recency and relative high resolution. And this took weeks, a couple months of work for the initial version 0 to train and then identify artisanal mining. And it's very good at picking it. It is a challenging problem, not the hardest problem out there, but challenging, especially across the Amazon, different parts of the Amazon. Later, we've applied foundation models, which I'll talk about, to make that even faster. I think Bruno will do a better job explaining what a foundation model is all about. But essentially, it is a machine learning AI model which has not been trained for a specific purpose. It's been self-supervised training, and there's different techniques that can be applied to work with satellite imagery. And Play is really is on the leading edge of figuring out how you structure your input data and how you process it to get the most out of a foundation model. But once you train it, you can then use it for multiple different purposes with a minimal amount of effort. This is the idea. We are still in the middle of the ramp up of discovery and innovation. So there's definitely indications this is a very promising avenue and that it has opportunity to drastically reduce costs and help everyone work much faster. But there's a lot of interesting challenges to figure out. For Earth Genome, we're really focusing on not on building, the foundation model itself, or sort of like trying to launch satellites and process that, work with that data. But, from the starting point of folks who are directly trying to solve problems in the environment, climate, make that connection and develop applications and uses of this data on top of foundation models that can be leveraged for, for directly having impact. This is another visualization just to kind of, I think, give a sense of like what's happening in a foundation model. So I'll let it restart again. This is Alabama, and basically in a foundation model, when we process, we take Alabama, put it into a grid system, and then each of those chips or tiles is processed using the foundation model into an embedding. It's a long vector of numbers. And the foundation model, through its training, has sort of, in some mysterious way, has built up some understanding of like the structure of what's in the image. And not just in the visible wavelengths with Sentinel-2, there's 11, there's many bands to work with, so it's also those non-visible bands as well. What is transforming there is kind of reducing that vector space into clusters, basically showing kind of once you reduce an image down, kind of compress it down into embedding, what things are close to each other, here just in a two-dimensional view of things. And as it turns out, if you do that, you'll see like those colors are then labels that were applied to the imagery. Say like here, I think we're looking at different kinds of construction sites. As it mouses over, it'll show you the different features. Here it's looking at runways, and here there's animal feeding operations. So within that vector space, the things which look the most similar are actually closest together, and because of that, you can build an application on top of it to find things which are similar to each other. That's what we're doing with Earth Index, to make this kind of Earth monitoring available for everyone. And the idea really is to bring a human into the loop that does not require having deep understanding of Earth observation and dealing with remote sensing data or machine learning. I've had throughout my career a real belief that the people who are closest to the problem have the deepest understanding, even if they're not highly technical. I've done a lot of work with OpenStreetMap, and I started humanitarian OpenStreetMap team and projects to like put data into people's hands. And I think that's part of our philosophy too, is that when data is as close to the problems as possible and the facility to use them, it has, that's not the only way, but that has like great potential for understanding and then connecting it to what's really needed, because there are people on the ground who are being directly impacted by these kinds of activities. I'm not going to do a demo because I don't know it's too complicated, but I'll just show you, this is just an animation of the application. I'm happy maybe after, if you're interested, I can pull up on my laptop and do a demo. But this is Earth Index, and this is doing this kind of monitoring and search. What we're looking at here is a region of Cambodia that we indexed, that we generated embeddings for. And then we're doing a search here just by labeling on the map here using, these are solar panels. And so the initial search just labeled a small area of solar panels, and then it then looked in that, did a vector search and found similar tiles. And this turns out to be an application. It's very good at finding them. So as it zooms out, you'll see there's a confidence score, which is sort of how near it is in that vector space. But you can see it spots other installations as well. And I guess the thing to say about this is like, we've released this in alpha, and we can make it available to you all to try things out on yourselves. We are really, I think our aim with this interface is really to, it's not simplify so that anyone can use, but someone who's, say, like, reasonably comfortable in Excel. Someone who's like knows their way around, can use this. And there's challenges to it because this is definitely an example of a search which works really well right out of the box. There are other searches which are more challenging. I searched for golf courses in Cambodia, and it found golf courses with that confidence. But it also turns out there's a lot of parts of the agricultural landscape in Cambodia which superficially, in embedding space, also look like golf courses. So we need to get, there is work to do to like help someone along a search to make it most effective and iterate. This one is a one-shot, labeled and it worked, but you have to iterate, provide positive and negative examples, and then it kind of tunes the foundation model. The work with Amazon Mining Watch has been directly used in reporting, in legal cases, in enforcement. We're lucky to partner with folks through the Pulitzer Center and other connections that we've made in the region, and so it's been great because it's helped to like center the work on make sure we have results which can be used right away. And we're starting to apply this. We've just released this in alpha, but we're already starting to apply this today. All of these dots are chicken feeding operations across the American South. So that's one close up. And we used Earth Index to build the most comprehensive open data set of poultry CAFOs. We've expanded it beyond these states at this point, because that data is not available, and it's, there's pretty critical impacts with poultry CAFOs, not as much with the emissions, but with water quality, environmental pollution. We're now taking the same approach to working on cattle CAFOs, which sort of look similar, but there's distinguished with cattle CAFOs primarily because the sheds are spaced out, and you see like ground which is stamped on between them, bare earth. And using Earth Index to find these globally. And the interesting when you go globally is they look different across the US, but also certainly like in Germany or in China. They're all, and they're also in different regions. Often in China, you find them in much more urbanized regions than you would find these cattle operations in the US. So yeah, so development data partnership, really important to know. You all are aware of the partnership. It's a very good way for folks within the bank and other development partners to get access to data. The data partners, when I was at Mapbox, it was great to like set up Mapbox to contribute data. There's a lot of commercial entities are providing data through the data development partnership that they're otherwise like only selectively selling on the commercial market, but apply to real development part. And we are making Earth Index and these kinds of searches available through the development data partnership as well. So it's one avenue if you would like for engagement for big projects, for technical teams, make a proposal. And yeah, interesting, like here's an example I was talking about, the Niger gold mining. It turns out it's in Sentinel-2, these are very hard to distinguish from other features in the Sahara. This is gold mining. It looks very different from the Amazon because not only the forest, there's no water, and there's basically kind of like a series of holes which are dug. And if you look at this in Sentinel, it's very hard to distinguish these sort of linear features from other linear features across the landscape. And it just looks like the wind is always blowing in one direction, and over millennia, rocks have kind of lined up, and maybe there's washouts occasionally that have driven things in a direction. So in this case, we needed higher resolution imagery, and so what we were able to set up through the development data partnership is Planet also makes data available through the partnership. So Planet gave data. We're now in the process of generating embeddings with that data and then doing searches with it, and early indications is having higher resolution imagery helps a lot. So it's great to be a part of that partnership where we can also get access to other data sources, and getting up the planet data is pretty can be tricky. So that's the end of my talk. Let me set up. There's my email. I'm really happy to talk about like what your applications you're working on as well. I don't know.
And then if anyone has quick questions now, but otherwise we'll do after mine.
Yeah, why don't you go ahead? Yeah, any quick questions, or we can. Okay.
Okay, so my name is Bruno Sanchez, and I lead Clay AI for Earth. Laura is here with me to defend this. The beginning of this presentation is the same as what Mikkel said, and you see there's some overlap in the things we do, and we can talk about after that. But that idea of Earth is telling us that there are a lot of problems like sustainability, climate change, extreme events, deforestation, fires, floods, and we are also collecting the data to see that. We've never had as much data as we have today with Sentinel, Landsat, Planet, others. Yet, we are not able to extract the value we know we can do, because it's really hard to do. It's really hard to do, and those of you here are GIS experts, it takes a lot of work. And we believe, that the missing piece to unlock a lot of value is this AI revolution. In fact, it's almost comical that from autonomous driving to language transcription to summary to all of that vision, they all use the same architecture, transformers. For the AI engineer, I don't know if there's more than one, but it's all transformers. And somehow there is no such revolution in geospatial. And I don't understand why OpenAI, Anthropic, and others are not doing it. And that's why we started Clay. Clay is the attempt to bring geospatial to these amazing tools. And this is the first slides. We see Earth telling us things are happening like disappearing lakes or receding glaciers, vanishing lakes, but it's really hard to extract the value from that. Things are getting better. A few years ago, Global Forest Watch was started, and it was an amazing tool to detect deforestation globally. Then a few years later, Global Plastic Watch, which you talked about, that Mikkel and partners did, and then Amazon Mining Watch was also done even years later. And the beautiful thing of all of these products that are tremendously impactful is that every time it's faster, cheaper, and better to do. These are not real numbers, these are just estimates, but you were mentioning that with those. It took a lot of millions of dollars and years to do the Global Forest Watch. Now, mining watch is much faster. So the question is, where is this going, and how can we get there faster? And how can we shape, especially in this context, how can we shape that progress development friendly, with development data, in development context? Both of us, Mikkel and I, have worked in developing countries, and we understand that it's a completely different talk that what happens in Silicon Valley. So how can we shape that? So that's the thing that Mikkel was saying. All of these tools traditionally are per tool an extremely painful, tiring, high-skilled processes where you get some Sentinel data, in many cases Sentinel data, pretty much a lot of things that use Sentinel data, do a lot of processing with a few people with a lot of skills, and then you get an output. You want location of mines, you kind of need to start from scratch again. And do a lot of processing, and do that. You want to do planet data, you need to do all that. This does not scale. And what foundational models allows us to do is to upfront do all the undifferentiated heavy lift. All of the processes, in all of the cases, we kind of need to understand what a pixel is, what a square is, what a green is. There's a lot of concepts that are common to a lot of the applications. So this is the foundational model. The foundational model takes data, pre-computes a lot of things, and I'll explain in a second to those who are not technical how this kind of works. And then sometimes you use it directly, Sometimes you do some fine tuning, which is basically tweak the model in a way that is better at something. Sometimes we have few loops of human feedback, like Mikkel was presenting, for exactly the location of mines, or you do some compute on top to do something else. But the key insight is that now it's much easier. Now it's much faster. And instead of having 10 teams doing 10 times this model with whatever, $1 million or 10 or whatever, why don't we make a non-profit to do this once, completely open, so that it's also open for business, so that we maximize impact. That is play. The what is what I said. The how is that we only touch open data, we only do untouched open source, and we license everything to be open for business. Because for profit businesses, we give them a multi-million-dollar model. We raise $4 million to do this, philanthropy money, so we don't need to recoup our investment, we need to open everything. So for companies, they get a free model to build amazing things with, and non-profits, tiny countries, and the bank itself can also benefit without all the headache of legal stuff or procurement or anything like that. That's why we created the non-profit to do that. So we trained the model, and this is some early results. The key, the game, is that all of this is using the same foundational model. And the way it works, well, I'll just do it in the next slide. But basically, today, we are releasing the version 1.0 of that, and this is some results. With exactly the same embeddings, which is this concept of the pre-computed and differentiated upfront work, we can get some data from this other non-profit of estimating biomass, and we can, in 20 minutes, we can predict with a 90% accuracy the biomass estimates that takes them much more time to do. So once we train the model on this data, we can get biomass estimates much faster offline without having to open the geospatial data, which is amazing. If you need 100% accuracy, okay, go do the other approach. If you're getting 90%, you have today open data, open source way to do that. Exactly the same embeddings, 90% or better line cover mapping. Exactly the same embeddings, two loops, two human in the loops, like Miguel was saying, 90% precision in detecting agriculture in Bali, Southeast Asia. And something that I'm also super excited about doing is human labels. And to explain how this works, I need to explain a little bit how the foundational model works. This is basically the same message that you have. But the idea is that, imagine that you are the foundational model. This side of the room are the encoders, and the other side of the room are the decoders. You get to talk to each other before starting, and then you get satellite images. You're experts in all the fields in the world, and you only got one piece of paper to write the summary of that image. You only got one piece of paper to write everything that is there. And then your task is to use that piece of paper and recreate the image without looking at it. So you are forced to condense, to summarize important things, regardless of what that image is going to be used for. Because if you're experts in forestry, you're going to write, oh, there's this type of forest, this, because they're also experts. If you see a road, you type the road. So that piece of paper conveys, after you train that, you do this literally billions of times. So that's why machines are better than humans to do this. And after you finish doing that, then you have a pretty good summary. So the image that you create is very similar to the image that you create, right? Are we all together? Are the AI experts in the room? Did I do a good explanation? That's unsupervised because there's no labels of biomass or anything. Now, one of the problems is that what is written on that piece of paper is not English or Spanish. It's just code. It's just vectors. That's the embedding that I talked about, numbers. So one of the things we did, which is these labels, the human labels, is that then after we finished, we took another group of experts to look at the image, but then took from OpenStreetMap, which is a map with labels of this text. We took that text, and then we did this. We made a summary of that text, which is the same as the summary of the images. So what you have at the end of the exercise is that one encoder that converts images into vectors, and one group that converts text of labels into the same embedding. So if I want rivers, I convert the rivers into a vector. I look what images are in that place. And that's how I find the images of rivers. This is an image to text encoder. That's how I allow you to do this. Spain is easy to convert into a region, but solar panels is because OpenStreetMap has solar panels in their maps. And we've done that exercise, and we know the embedding that corresponds, the cluster that Miguel was showing that are solar panels. This again is open source, open data, you can use that. And when we train B1, please ask me technical questions on the summary. B1 is a mascot encoder, for those of you who don't know what it is, with dino losses, to train with 70 million images. It can work with any resolution or any instrument. We train it with Landsat, 30 meters pixel, Sentinel, 10 meters pixel, NAVE, 1 meters per pixel, and New Zealand is some drone data set, like 5 centimeters per pixel. In RGB, infrared, synthetic radar. So it can absorb any of those, any band, and then creates the embedding of those. It was trained like last week. That's why it's pretty latest. It's already available in Face if you want to download it, and the documentation is coming up soon. This is the idea. I forgot I had this slide, but this is what I explained. You have the image, you make the vector, and then you collect all of these tags: commercial, build, highway, plane, whatever it is, and you train the model to put it in the same place.
Is this collection, does this collection need the human, or is it automatic?
It's all automatic. It's all automatic. We take the OpenStreetMap data. It's a limit because it is as good as OpenStreetMap is, but we have proved that we can do this. So if we have other labels, we can do the same thing. If you have other descriptions, we can do the same thing. That's also the beauty of the model, is that it is trained with all of that global data from open source only. If you have access to Planet, you can continue training model, and it's going to be able to create more clustering of using that high resolution. So that's the continuous training model. So we are not only creating the encoder of text, we are also working to integrate it into Jupyter. A lot of data scientists use this environment of Jupyter, so it's called Jupyter AI. It's designed for language models, and that's why we have to build that bridge. But later this year, we will announce this integration. We are not only about the model, we are driven by operational use. And because we're building operational use, if you are a developer and you know how to do these things, go take the model, do everything you want. It's fully open license, open code, and wait. For the rest of the world, which is odd, the geospatial analytics market is estimated to be I estimate it to be 1 million users, because Esri is one of the leaders. They say they have like 500,000 to maybe 1 million. So okay, let's double that. 2 million people can understand and do these things. We don't want that. We want 100 million or billion. Ben, a colleague of yours in Genome, was showing yesterday that the beauty of ChatGPT is not that it's technically better, is that they made it really easy for everyone to use it. So we want that with this. An Earth index, and which is kind of the equivalent in that sense, is to make that happen. So we have 2 apps that allow users to not need anything. One is to create embeddings. If you have a region, time, an instrument, to create the vector embeddings, and then you can do everything, anything you want with it. Currently it's only Sentinel, but we aim to expand it, and I can do the demo in a second. And the other app is essentially similar to what also Miguel was showing, of click, point and click, and similarity search to do that. I'll do the demo in a second to show how it is, but the last bit is that I can say that Clay is the best AI for Earth model out there. I have my reasons for that, but what does it even mean? Everyone can say that. We don't have a common framework to evaluate why and how a model is better. We have the same for text. We have that for text. There's a lot of metrics. We don't have that for geospatial. So that's why because we want to see that change happen, we partner with Geospatial, with ESA, AWS, Clark University, Development Center, and yesterday there was these 10 other institutions who also wanted to join this working group to help define the benchmark. And we think that a good way to force the progress of this benchmark is to create a competition. So we also have today a competition of $10,000 to make the best open model even better. If it's clay, we give it to someone else. But if it's not clay, we give that model $10,000 to make it even better. And one of the things I want to highlight, especially in this room, is that what makes a model best, in some ways, is an objective score, F1 score, whatever thing it is. But in many practical ways, that doesn't matter that much. What matters is that, is the model open license? Can I run it in a small computer? Do I need the internet? Does it work with data that is from, I don't know, commercial data? Does it work with data from Africa? Like, there are subjective or application-specific criteria. I want your help to help define what that is, and then help to make that the best model. Not because I say that, but you choose the model that is convenient for you. And I'm going to do quickly a demo. So it is not open yet. So build is the thing, build.made with play. We'll do demos every couple of weeks. You can sign up on our website. And play.org, but of course you can, through Holly, you can reach to us. Use this password. ITS is probably freaking out right now that I'm doing this. It's a very MVP. A big difference between this platform and Nickel's platform is that they have worked with this for years and they have a lot of projects to work with. We are starting, things break, and our ambition is to, of course, keep improving it. The idea of the builder, as I said in the beginning, is that you need embeddings for a place, and then you go here to make the embeddings. This is, for example, I selected Albania, and I created embeddings for Albania. I want to make a new one. Is there? I don't remember how to make a new one. Here we go. So let's make one for Bhutan. So let's make one that is corrected, and this is going to be Bhutan. Search the country. Okay, so this is the region. I can add things, remove things, whatever it is. Right now, it's only Sentinel, only 1 year. We want to make it custom so you can use, there you go. You can choose which version of model, with which data. And here we have the option of doing the Sentinel or doing with Nave, and the size of, it doesn't really matter much what this means, but basically you can create these vector embeddings. And then you click yes, and then it's going to do it, and it takes a while. And then after it finishes, you can download it, you can do whatever you want.
Sorry, what is that you download? What type of file you download?
It's a vector. So that is the piece of paper that I said in the summary. It's called embeddings. This is a very large vector. It's like 768 numbers, which have absolutely no meaning to humans, but convey all of that stuff. It's a mathematical summary of the image. So you need an interface to make sense of it. And that's the interfaces that index and this is. And then the other one, to make it really quickly, because we are really running out of time, is Explore, which I have the link here. Copy. And out fire. No, ask me for the ask me for that. Ask me for the explore, play the Lord. Why is it not asking me for that? Sorry that this doesn't work. It should ask for a like a window, pop-up window to the authentication. I'm sorry that. Is this because it's in private mode? Let's see. Explore, play with clay, the dog. It's weird. Anyone knows how to fix that? Oh yeah, that's a good idea. But we need to make it.
It's on clay.
Yeah, but I don't know if we can navigate LinkedIn without being.
Yes.
Yeah. Okay. Fine. I think we have. I'll try to figure out how to do it, and I'll send otherwise the link through Holly, so you can take a look. It's the same idea as the Earth Index. It's point and click. It's more experimental in a sense for that. Yeah, if you are interested in working with us, then reach out directly or through Holly. The summary is this clay model available today in Hugging Face, all open data, open source, open license. Text to Earth available today, open data, open license, blah, blah, blah. Clay Builder and Clay Explorer, early access now. We have every 2 weeks that. The reason we put it in early access is because we know it breaks and we want to know how it breaks to fix the errors. Jupyter integration later this year, and the benchmark and working group announced today. So thank you.
That's a question. So let's say you download your map of Washington, D.C.
Yep.
And then you can say, look, I'm in this part of the city, what's the tree deforestation, heat index in the summer, that kind of stuff as well, where you say, okay, it rains, there's a storm, what's the flooding impact? Like combining all that, you can download it already in the city.
You can take the model and then take the data and make embeddings, and then you are here in the diagram. Or you can go to Clay Builder, which does this for you, and then you end up in the same place. You end up with a bunch of vectors. So you still need a tool to convert the vectors into rain, heat, or whatever thing it is. You still need to do this. It's way less. It's like 0.01% of the size, 90% of the colors. Let's say it. Or you can use it directly this up. That you still need. It's still a technical resource. The only non-technical tool right now to use embeddings, as far as I know, is the two tools that we are presenting today.
My question is the embeddings that you're using, are they applicable in estimating, where there's data gaps in data the input data that you're
Like clouds, stuff like that?
Yes, yeah, where there's cloud coverage.
Bro, yeah, I think my intuition is that the semantics of that will be strongly there. So yes, the answer is yes.
And one question to that is, if you're doing that, especially in regions like where there's a lot of smallholder farming, like farms where there's like the boundary lineation is very like confusing. Like, is your model able to help with that?
So right now, the semantics, if you know what that doesn't see much, but right now the semantics are at the tile, at the image, at the tile image. You have an image and it's the semantics of the tile image. You cannot make the semantics of a specific sub-region unless you make the chip very small. You can do that. Clay 1.0 allows you to make an embedding only of the square of that. But also, if you know how to work with that, you can take the encoder, this side, and make a dense decoder to do a segmentation task. You can still do a segmentation task now, but that segmentation, I think, doesn't convey the semantic meaning as if you do decoders. Short answer, yes, but you need to do some work.
Yeah, it's a R&D area for us as well, because once you identify something, say like the CAFO example, if you're going to do emissions modeling, you actually need to know the footprints of the buildings and the footprints of where the animals are. And from that, you can build an estimate of the number of animals, and that then goes into the model, how much methane they produce through digestion. And what we're exploring is that kind of connecting to processes. The first pass, find where they are in the tile. Then the second part, segmentation. What we're experimenting with are things like just purely image-oriented models. We're looking at segment anything in particular to develop a workflow where you still have a human in the loop, making sure that those boundaries look correct, but that you have a leg up by something which can interpret what's in the image and at least do a pretty decent first pass and accelerate the human process of doing segmentation. So something like for us, Earth Index would output those locations, and then we're looking at another workflow to make go from someone who is hand digitizing all of those to someone who is still looking at them to make sure they're right, but has a process that makes that just as easy as kind of oh yeah, that looks good, accept. No, that's something. Yes, yeah. And then if there were some which the automatic segmentation didn't do a great job, then go to human labeling. I mean, Bruno talked about a lot. If you get 90% of the way there, you're 90% of the way there. So you've got that. If you still need to spend 10% of doing human analysis or digitization, that seems you've reduced by 90% the amount of time. So that's kind of what we're working on that.
So I have a question. You said something very interesting, one of you at the beginning, about the closer the data is to where the problem is, the more impact it has. So, and these tools are meant to be used by people who don't have who are not highly skilled in data processing, modeling, and so on. So, but and then in some parts there is the problem of connectivity. So these models have to, because they process a lot of data. Do they need to run the processing? Does it have to happen in the cloud? Can it happen in a local computer? What are the requirements for these local processing?
The current models we get currently, everything is in the cloud. So sort of running the front end, there's a straightforward path to say how that could run. You could just have that hosted, running locally. The back end, the search, the API, that today, no, but that's it's an interesting point.
No, because you were showing images of the Amazon, and I was thinking of local communities using, but there's no way.
But you don't need to load the images. It's a very thin line. It's a very thin connection.
No, but the images are in the cloud. They cannot access the images if they don't have connectivity.
If they don't have any connectivity, true.
Yeah, there's ways around that, and there are people who are but you have to architect differently, and there are folks who spend a lot of time working on data creation and management, totally disconnected, but then when you do have connectivity, sort of linking it up. And I'd say for us, where we position ourselves is the groups which are maybe they're one step away from the folks who are completely disconnected, or allies or supporting organizations working very closely and having trusted relationships with indigenous groups in the Amazon who are working on those kinds of data creation and management issues. But there may just be pieces of that where you have to go and have the connection, but then the results from the search are not, they belong to the person who searches for them. They're not broadcast out on the internet. So you can download the results of your search, GeoJSON, very portable, and then bring that into a different environment for where maybe there's been on the ground data collection, and that could all be brought together in a seamless way offline. So there may be some, maybe some combination of things to get there, and that's why we've kind of worked with the folks who are still data experts but are really very much in the field.
With Clay Explorer, it's the same idea, but the model, if you don't have any connectivity, if you have a computer with 500 megabytes, you can do exactly the same because you don't know the model. And then if you have the embeddings, you just use the embeddings. You don't need anything. Like you go to the capital and you work in this region, you just don't know the embeddings for the whole region, and you have the summary, which is like maybe 100 megabytes or even less, to do everything, to do heat island, station, similarity, everything locally. But also, if you have the images offline from drones, you do a drone mapping exercise, like I did when I was in the bank in Kosovo or something, and connectivity was bad. If you have 100 megabytes on your computer, you directly pipe the drone images to the model completely offline, and you get embeddings. You need to go back to the capital to do that.
The trade-off that you need, if you're going to run it all offline, you need to have a little bit more of the tooling and the facility to work with the data in your local environment. You certainly can do that, but that's a trade-off. It's not as easy.
It's a technical resource. You need a technical resource.
Yeah, just a question. I mean, there was mentioned the type of data you can use. I mean, what kind of level of pre-processing do you need? I mean, it was mentioned about cloud cover and that sort of stuff. I mean,
you want to go first?
Just to say, on cloud cover, we do a lot of work to, especially to process, a time period to a cloudless.
Okay.
We just did that for all of 2023, and we did a global cloudless composite.
So that needs to be done before you apply the model. The model doesn't actually. It's
that's how, for clouds. That's what we do pre-process, and we've made that cloudless composite available. So I didn't realize, you think that's the kind of thing that already existed. You could just do a Sentinel-2 cloudless 2023. No, it doesn't. It had to be done. So that's now out and available. But you have to pre-process it.
So for us, we took 70 million chips of Landsat, Sentinel, Naves, and others raw. I mean, not raw, level 1. So they have clouds, they have all the stuff. So that's why we have 1 to 10 images per location to account for those things. If you don't have, if you throw composites to play, it's better because it doesn't need to deal with clouds. But if you throw images with clouds, it will also do the embeddings and will embed the clouds. So it can deal with both of them. Or if you have synthetic radar, we can also throw synthetic radar and we'll give you an embedding, which doesn't suffer from clouds.
Other questions? Great. Well,
from my side, what I'm looking for is if you have specific areas that you're interested and specific sensors, if you don't have data, but it's Landsat or Sentinel or Nave or whatever, and regions, tell us. We don't want to create embeddings for the whole world until we know Clay is good. But if you say, hey, I'm working in India, okay, that's not good for India. I'm 2022, 2021, Landsat, Sentinel, whatever thing it is. What we are desperately looking for is operational value. So if you are working in projects that could use these embeddings, especially if you know how to work with embeddings, which is people tell us, hey, can you do Niger? Can you do this? Can you do that? In Landsat, in Sentinel, in 2020.
But potentially, could it work global level?
We run embeddings for the entire archive of Sentinel and Landsat for 12 petabytes. But we don't want to do it until we know it kind of works, because maybe there's a tweak we can do in the model, and we run the training. The training is probably took $500,000. So if I'm running the whole world, it's 100K, 200K, substantial amount of money. And we don't want to retrain unless we have to, and we don't want to redo the embeddings unless we have to. So that's why we are desperately looking for your how and when it breaks. So we can try to fix it, to make the embeddings, and provide embeddings.
The use case for global search and monitoring is also an interesting one to think about, just given the diversity of any particular thing, how it looks different across the world. So it's also, even with a global set of embeddings, is the need to search for something globally, or is it the ability to search for anything in particular areas, but do it just anywhere on the fly?
This is a screenshot I was looking for. It's basically similar. Things one.
but in our experience, like things look very different in different regions, and so it's something, it depends on the type of thing, whether in the use case, whether global search would be effective. But yeah, I mean, just to echo what Bruno said for us, what is the challenge? What data are you trying to get? What problem are you trying to solve? That needs to be the orientation for this kind of work. Otherwise, it's all pie in the sky, and that's not. There are a lot of problems to solve, and so if you have some of that, we want to hear from them, and see which ones we can help with. Cool. Thanks, everybody.
Thank you very much.